Hello everyone, I'm glad to present our paper, Machine Learning with Differentially Private Labels, Mechanism and Frameworks. This is a joint work with my amazing collaborators from Princeton University and UMass Amherst. First, let me introduce the definition of label differential privacy. We call a randomized mechanism M with domain D, which includes feature set X and label set Y, to preserve epsilon delta label DP if the probability of outputs for any two label labeling datasets are similar. Here is an example of the label labeling datasets, where we can see that the feature sets here are all the same, while there is one label Y3 differs in the label set. We now understand what is label DP. The next question is, why do we study label DP? Label DP fits for several practical scenarios where features are public while labels should be kept private. One example is ads ranking, where the ad tag knows the ads content delivered to the user, which can be regarded as public feature. However, the user's interaction with the ads content should be kept private. Another example is some sensitive survey, which may ask questions about income or medical history. In the meanwhile, the profile of the participants, such as gender or race, might be public. As label DP only requires label to be private, we understand that if a mechanism M preserves epsilon delta DP, then it also preserves epsilon delta label DP. Therefore, we can use current DP techniques such as DPSGD to achieve label DP. The problem is that DPSGD may suffer from a loss of utility. As label DP is a much more relaxed form of privacy, where only label is private. The key question we'll ask in this work is, how can we optimize utility with this relaxed privacy restriction? Our work on label DP focuses on how to improve the utility. Specifically, our key insights are twofold. First, we can leverage the public feature information to denoise the private labels. Second, we will also leverage the most recent advancements in machine learning to further improve the utility. Our framework leverages unsupervised learning, semi-supervised learning, and learning with noise label techniques to add less noise and also reduce the effect of noise. Besides, we also make a comprehensive comparison with existing works and also make specific recommendations regarding our framework. One good property for differential privacy is proofs processing, and this also holds for label DP. That is, if a mechanism M prime with domain on the label set Y and also range in Y satisfies epsilon delta DP on Y, which also implies label DP, then for any other mechanism M which take X and M prime Y as input will also satisfy the epsilon delta label DP. Based on existing works on how to generate the differentially private labels, we can proceed to focus on how to improve utility. We use two existing differential private label generation. One is a randomized response, which probabilistically replaces a true label with a random label. The second one is party-fixed match, which is a variation of the party framework. As the label DP allows the feature to be public, the party-fixed match will use the same public feature to query the teacher model and train the student model. Same as party-fixed match also benefits from the flexible number of queries of the privacy utility trade-off. That is, the fewer queries, the lower epsilon. Party-fixed match is used as one of our pipeline, which is pipeline 3. I will introduce the pipeline 1 and 2 in the next slides. To generate the differential private labels on the whole training set by party-fixed match, we will query the student model to generate such labels. Our first pipeline is based solely on unsupervised learning, which can add less noise compared to directly adding noise to the individual sample. When thinking of the label privacy, an easy approach to protect the privacy of sensitive label is to not use them at all. Therefore, we consider clustering. After the clustering, we still need to assign a label for cluster, so we still need some label information. We propose a noise cluster, which adds a Gaussian noise to the class count for each cluster on the true labels, and then does the majority voting. Here is an example of the two classes case, where all the points here are with a true label. That is, the blue points are with true label blue, and the red points are with the true label red. After the unsupervised learning, we have two clusters, where cluster 1 has most blue points and cluster 2 has most red points. Let's look at cluster 2. We know the counting in cluster 2 for red versus blue is 18 versus 3. We will then add a Gaussian noise to this counting. After the majority voting of the Gaussian noise counting, we can get the cluster label for each cluster. As the cluster 2 has the most red points, the majority voting of the Gaussian noise counting is likely to be the majority voting on the noise-free counting. Here is an overview of our pipeline 1. We will first do the unsupervised learning to get a cluster model. We then generate the clusters, and after that, we will apply our noise cluster algorithm to assign the cluster label on the cluster model and get our final model F. During this process, no noise is added to individual sample, and after the unsupervised learning, no learning process is further needed. Our second pipeline focuses on how to reduce the effect of noise based on existing advancements in machine learning. The noise cluster has a limitation that its performance is bottlenecked by unsupervised learning. That is, even when epsilon is very high and gives almost a true label as private label set, the noise cluster will still have the same performance as unsupervised learning. We propose denoise SSL, which combines unsupervised learning and semi-supervised learning. Our strategy is that we will only select samples which have same noise label and pseudo label. The noise label is either by randomized response or party-effects match, and the pseudo label is by the majority voting on the count of noise label set for clustering, and no extra noise is added in this process. Here is an example. The points in this blue area are always a true label blue, and the blue points indicate that there was true label, while the red points indicate that there was a noise label red. We also had a pseudo label set by the clustering, which may assign most points as blue but still several as red due to the performance of clustering. By comparing the noise label set and the pseudo label set, we can find a mismatch in these sets, and we will remove these mismatch points. We can see that compared to the noise label set, the output of the denoising is a smaller label set but with a higher precision. As we still have the full public feature set, we will consider semi-supervised learning. Besides denoise SSL, we will also consider directly leveraging recent advancements in machine learning beyond the standard optimization. We consider LDP SSL, which directly applies semi-supervised learning on the whole training set. Specifically, we will use fixed match. We also consider LDP LNL, which will use techniques from the learning with noise label techniques. This is because the model learners can learn more label information during the training process, and the learning with noise label techniques can leverage such label information. Specifically, we will use the arc descent. Here is an overview of our pipeline 2. We will generate the private labels either by randomized response or party-effects match. We will also do unsupervised learning to generate the clusters and then generate the pseudo label. After that, we will train the machine learning models under label differential privacy either by standard optimization, semi-supervised learning, or learning with noise label techniques, or our denoise SSL. We conduct our experiments on 3 benchmark datasets for image classification, CIFAR10, CIFAR100, and CINIC10. The number of classes vary from 10 to 100, and the total number of images vary from 60,000 to 270,000. We consider models including 318, VGG16, and WideRaceNet with 28 and 4. We first evaluate our pipeline 1 noise cluster, where we can say that the noise cluster performs well at small epsilon. For example, on CIFAR10, even when epsilon is equal to 0.003, while the randomized response only gives a label accuracy of 10.03%, which is close to totally random, the noise cluster can still have the high performance at 88.3%. And this is also true for CIFAR100 and CINIC10. We next evaluate the denoise SSO and LDP SSO in our pipeline 2. So here we compare the noise cluster and denoise SSO and LDP SSO combined with randomized response. We can see that while the noise cluster keeps the same performance at all reported epsilon, which is 88.3%, both the denoise SSO and LDP SSO increase the performance as epsilon increases. Besides, the denoise SSO always has a better performance compared to noise cluster at all reported epsilon, and the LDP SSO is better than noise cluster at epsilon equal to 4. As for the party-effects match as our pipeline 3, we can say that compared to randomized response combined with denoise SSO and LDP SSO, the party-effects match is always better than these two approaches on the randomized response. This is because the prefix match will benefit from the choice of flexible number queries to add less noise. We next evaluate the LDP arcdescent in our pipeline tool, which is learning with noise label techniques. So here we consider the randomized response or prefix match combined with best performance of other approaches or the LDP arcdescent. We can see that LDP arcdescent performs well in most cases except for epsilon equal to 0.5 by randomized response. Besides, when epsilon is is lower, the best accuracy is from the prefix match combined with LDP arcdescent. This is because the prefix match can provide the label set with higher accuracy. When epsilon is high, the best accuracy is from the randomized response combined with LDP arcdescent. This is because randomized response can provide more label information. We also make a comparison with existing works, and we can which is Alibi and LP1ST random prior. We can see that our work is better than the Alibi and LP1ST at all reported epsilon. Besides, we can also observe that the utility of advantage of our work decreases as epsilon increases, though at epsilon equal to 4, the utility advantage is still significant. For more experimental results, please check our paper. We finally make recommendations on how to maximize the utility of our framework. When epsilon is extremely low, please consider noise cluster. If abundant computing resources is available and with a high label cardinality n and with low epsilon, please consider prefix match. Without above specific conditions, choosing randomized response can make sense simpler. Specifically, when epsilon is high, you can directly use standard optimization and randomized response already get the label set of high accuracy. When epsilon is low, you can consider denoise algorithms such as denoise SSO or arcdescent to reduce the effect of noise. That's all. Thank you for listening.